another demonstration, which is most remarkable. Remember, I'm talking about the expansion of gases and liquids. Now, water has strange properties, and I'm going to do a program, a show, a lesson on water alone. But for the moment, here is a chamber made of 1/4 inch thick iron. Now, I'm going to imagine that we fill that completely with water. Completely. That means that the occluded gases in the water must be driven off. We could do that by warming the water gently. Now I'm going to stopper this up with a screw cap very tightly so that we have water in here and nothing else, no air, no other gases. Now let us imagine that I take this iron bucket and I put this ice bomb, as we call it, in there, and then I load this with ice, to which I could add some salt, because salt depresses the freezing point. You've made ice cream, I'm sure, by adding salt to ice when you ground away at the cream. Now what happens? The water gets colder and colder and colder, and now a strange thing. We cool it down from 8 to 7 to 6 to 5 degrees centigrade, I'm talking. And now at 4 degrees centigrade, it has its maximum density, which is a strange thing. And then we go to 3, colder, 2, colder, 1, colder, 0 degrees, and it freezes. Remember, it was most dense at 4, but it freezes at 0. So the water in there freezes. Now, what happens to water when it freezes? It has, as we say, anomalous properties. Strange and uncommon behavior. It expands. And the forces of expansion are thousands, tens of thousands, hundreds of tons. And this is what happens to that bomb that I have just described. Rent apart. Indeed, it is very dangerous to do this experiment, because sometimes the pieces of the iron chamber pierce a hole right through the wall of the bucket and could hurt you. This suggests the enormous forces when water freezes. Now, expansion. Consider these 2 little chambers that I spoke about before on an earlier program, and they failed to work as properly as I wanted because they were at too high a temperature because of the lights in the studio. A volatile liquid, let us say acetone or ether, the chambers have been drawn down a little and evacuated so that I have the vapor of the liquid there. Now I'm going to apply some thermal energy from my hand to the vapor right there. Watch it now. Look at that. There it is. Notice the tremendous increase in pressure of the vapor. The expansion of the vapor drives it over. Here is a bigger one of the same thing. Oh, look at that. Look, isn't that incredible? Look at that. I had this in a chamber in this bucket with ice so as to cool it down. Let me warm it up. And look what's happening. Look what's happening. The increase in pressure, the expansion of the vapor, driving it over. There it is. And doing enormous work, of course, in raising this liquid above the 0 potential plane. There it comes back. There it comes back. And I shall not worry you further with that. Let's take another demonstration. A balloon. A balloon. Some air in it, and then it's tied off. I'm going to try this. This is wonderful because often it doesn't work, and I like demonstrations that don't work. Here is a mecha burner, something like a Bunsen burner, fed with some propane gas, and here is a flame there. I'm going to try to heat this, and if we can get close with the camera, I hope to see an increase in the size of this balloon. Oh, well, whether there was an increase or not, I don't know, but it was fun. You see, people, ladies and gentlemen, and boys and girls, I said what? I said it was fun. I can do this work only because it's fun for me, and that's why it has been so easy to do. So I suggest that some necessary ingredients of your life and work be imagination abundant, Good health, of course, you need much of. Otherwise, you are useless. But then you must have fun at what you do. Consider this experiment. I call this my Julius Sumner Miller earthbound rocket. Here is a steel pipe, one end of which is capped off very tightly, steel pipe, and it's on a wheeled affair so it can roll. Now what do? I put some dry ice in there. You know what dry ice is. Dry ice is solid carbon dioxide, solid CO2. I put some in there, jam it in. Then I put in this stopper, tightly fitting. Then I let it stay here on the table and let some time elapse. Now you know what happens to the solid CO2? The solid CO2 goes to gas. As a matter of fact, it has strange properties because it doesn't go through the liquid state. It goes at once from the solid to the vapor. And we say that it sublimes or sublimates. Let's think of another thing that does that. Oh, camphor. You put camphor. What is camphor? Dichlorophosphobenzene or some such stuff. You put that in your clothes, in your closet, and it disappears without leaving any sign of wetness. So anyway, the CO2 in there goes to gas. Gas, gas, pressure, 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 pressure. What happens? What happens? Out goes the stopper, and this earthbound vehicle of Julius Sumner Miller vintage goes the other way. This, of course, is a demonstration of Newton. But what I'm talking about here and now is the tremendous expansive properties that arise from the expansion of the CO2 vapor. Now, I had set up here a demonstration commemorating the work of our beloved Michael Faraday, his air thermometer, which I invite you to do. We are having a little trouble with it because we are working here under uncommon circumstance with much light in the studio. But here is a flask and a one-hole stopper and a tube, and the lower end of the tube is in this colored liquid. Now, what did Galileo discover? Galileo discovered that the level of the liquid comes up and goes down according as the temperature in this goes up and down. Now, strangely enough, you see, he was not measuring temperature change, but rather pressure change. And so I hope you will investigate the wonderful work of Galileo Galilei, and I thank you for watching.